All right, in this last video in our reaction energy chapter, we are going to talk about the driving forces of the reactions. And I don't mean like literal driving, I mean like how do we know if a reaction is going to happen spontaneously on its own? Well, like we know that in real life there's certain things that we can predict. We know that a ball is always going to roll downhill, it's not going to roll uphill. But why? That's because of the driving force that determines that the potential energy is too high to go up the hill on its own. Nature wants everything to be as low energy as possible. Energy and heat and temperature will always flow from an area that is high down to low. Sound similar to something you know? Yeah, like diffusion. That way you get these things to happen spontaneously so that things are kind of all evened out. Mother Nature is chill. She's the literal first tree hugger. All right. Nature has a tendency for all these reactions to go to a lower energy state. All right. So, what we're going to go over here is another term called entropy, and possibly my favorite of all of the terms in chemistry, because entropy is a property that describes the order to things. And guess what? Nature doesn't like things ordered in a nice, easy, predictable way. It likes chaos. It likes disorder. I mean, ask yourself, what's gonna take more energy to clean up your room or to mess it up? You can destroy your room in a hot second. Your dog can eat this couch and sit on it and be like, what? It wasn't me. Look how cute I am. Okay? But this cat, same thing, is not gonna make sure that this paper towel. Oh my gosh, this happened to my cat one time. He got a roll of paper, toilet paper, and went all over the place. Ugh. All right. But it is going to take more energy to order it and put it back the way that it was than it is to straighten up your room. Okay, so we actually refer to this as delta S. We're going to refer to this as the change in entropy, and it is in joules per Kelvin and mole or mole Kelvin. All right, that means temperature is going to affect entropy because guess what happens to our nice, organized, lovely little ice molecules? If I heat them up, that ice is going to form water, and you're going to see that it's going to be all flowy and chill and cool. And if I heat it up even more, then it's going to make the gaseous vapor, which means that it's mainly empty space, and those little suckers are flying around all over the place. All right, so entropy is going to be one of the factors that we use to figure out the overall energy of a reaction or a process. So we refer to this as Gibbs Free Energy. Okay, it depends on two things: the enthalpy, the delta H of the reaction, which we went over in Hess's law in the previous videos, and the entropy, which is determined by delta S, also in a appendix table, and the temperature of your system at that situation. So at some points, you can see that things will be either spontaneous or non-spontaneous, totally dependent on the temperature. So it takes energy to melt ice, but if you don't have enough energy, it's not going to melt on its own. So we use Gibbs free energy equation to determine that enthalpy, entropy of a system. So you're going to see this written as delta G for our Gibbs free energy is equal to the delta H minus the temperature times the delta S of the substance. Okay, so delta G, okay, and the H and the T and the S. Doesn't this look like the Abington School mascot? Okay, so I call this the ghosts equation. So here's your G, your H, your T, and your S. Okay, G, H, T, and S. And you can see that there's that big blank there so that you know that it's the delta H minus the T delta S. Okay, some people like to add the delta sign as an A and call it agatas. Agatas, if you want to use that to remember what the equation actually is. But our delta H, if it's negative, you'll see that it will be favorable and it will spontaneously happen on its own. If it's positive, it will be unfavorable and non-spontaneous. So you will have to increase the amount of energy in the system in order to get the reaction to occur. Okay, and if you see the little degree sign, don't forget that is our new standard temperature at 25 degrees Celsius because 0 degrees Celsius is super cold. All right, so this little table here kind of summarizes the whole thing. When you're going to see things be spontaneous and when we're going to see things be non-spontaneous. So it's delta H minus T delta S. So basically, we are subtracting these two values in order to figure out what our Gibbs free energy is going to be. If we have an exothermic substance and we have a positive change in disorder, so we see things that are going to become more random, you will always see this be negative. So that means that this will spontaneously happen. Okay, on its own, it's not going to take any sort of effort. All right, if you have an exothermic reaction, but you're actually decreasing the disorder, then you're going to see that it is going to be negative at your lower temperatures. Okay, so we'll only be spontaneous at low temperatures. If we bump up the temperature too much, it's going to increase this total product and therefore make it be non-spontaneous. Okay. So, similarly, if you see an endothermic substance that is going to have a disorder happening, okay, it depends on the value of your temperature. If your temperature is high enough, yeah, then it'll be spontaneous. But if it's not going to be a high enough temperature, then there is no way, Jose, that that is going to happen. And then lastly, okay, if you have an endothermic value and it's less random, there is more order than disorder, then this will never, ever, ever be spontaneous. So this will not happen on its own and what we refer to as non-spon. Okay, so let's calculate some values here. All right, so here is our reaction. Okay, we have ammonium chloride, NH4Cl, reacting with or decomposing into NH3 and making some hydrochloric acid. This is going to occur at 298 Kelvin. Our delta H is determined to be 176 kilojoules per mole, and our delta S, which we would get from an appendix, is going to be 0.285 kilojoules per mole Kelvin. So calculate the delta G and tell me, is it going to be spontaneous or non-spontaneous when we mix this stuff together? All right, so will this react on its own? So we use the delta G equals, um, since we're at 0, 25 Celsius is the same thing as 298 Kelvin. We know that. Delta H minus T delta S. All right, so what is my delta G value going to be? Okay, the delta H is 176 kilojoules per mole. And our temperature is 298 Kelvin times 0.285 kilojoules per mole Kelvin. And we are going to see that Kelvin and Kelvin will cancel out. So we then can use our calculators, go get them, come back. 176 kilojoules per mole, and then minus this product right here, which is going to be 84.9 kilojoules per mole. And once I subtract that from here, my delta G is going to be 91.0 kilojoules per mole. So what does that mean? That means this positive value means that this is going to be non-spontaneous. This will not happen on its own. This substance will not decompose on its own at this temperature, at room temperature. Okay? If we make it warmer, okay, if we increase this value here, it will raise the value of the product. And as long as we can get over 176 kilojoules, guess what? Then it would turn spontaneous and it would happen on its own. All right, so to review, we have our GHOSTS equation, our delta G equals the delta H minus T delta S. We get 176 and 298 and 0.285, getting a value of 84.9 kilojoules for this product right here. And then we see that this is a positive value, so therefore it is non-spontaneous, not going to happen on its own. All right, ladies and gents, that is our entropy and our Gibbs Free Energy.